Hello everyone, today I'll be talking about aqueous solution properties. In the next video, I will go through the reaction in aqueous solution. I will provide a link in the description of the video to download the material. Solution is a mixture of two or more substances. Solution itself can be solid, like alloys, liquid, like seawater, and gas such as air. We have some terms that we use in describing solution. First, we have what we call solute. Solute is a material that is presented in a little amount, while solvent is the material that or the substances that present in larger amount. If the solvent is water, we will name this solution to be aqueous solution. We have three types of solution. Either we have unsaturated solution, or we have saturated solution, or supersaturated solution. If we have amount like 30 grams of sodium chloride that we can dissolve in 100 ml of water, we will find out that if mixing both of them will give me a complete dissolved sodium chloride into water. While if I add extra 10 grams, this means I try to dissolve 40 grams of sodium chloride in the same 100 ml of water, I will have some material left. This material which deposit means that my solution is saturated solution, and any extra solute is added, it will not dissolve in my solvent. For supersaturated solution, I have example here for sodium thiosulfate. When I dissolve sodium thiosulfate, I'm only allowed to 50 grams per each 100 ml. But if I try to dissolve around 993 grams of in 100 ml of water, if I heated my solution and tried to dissolve this amount of water, it will dissolve completely. If I cooled down slowly my solution will remain clear. But if I add extra amount of sodium thiosulfate, the solution will start to just collapse and crystalline dramatically. So for any substance, we describe the solubility to be the amount of solid that dissolve in a certain solvent, and it will depend on both of them, on the solid and the solvent. The solubility and the saturated solution. For solution, it will be completely saturated if there is an equilibrium with respect to a given dissolved substance. This means the amount of substances that is dissolved is equal to the amount of substances that is deposited. If I try to explain the solubility itself, we can explain it according to the rule like dissolve is like. Oil is immiscible in gasoline because both of them are hydrocarbons. If I have water and I try to dissolve some oil in this water, I will end up by having a layer of oil over the layer of water. The oil will just float over the water because it have less density than water. Both of them will not mix together because both of them doesn't have the same property. For oil, it is non-polar, but for water is a polar solution. So if I try to dissolve any material, I will only be able to dissolve polar substance in polar solution to get miscible solution. Or I can dissolve non-polar substance in non-polar solution, like here in oil, in gasoline, to get miscible solution as well. But if I try to dissolve non-polar with polar, I will get immiscible, which means it doesn't mix together solution, so solution of 2 layers or more. So there are few factors that can limit the solubility. Those factors, like I said before, will depend on the solute and the solvent. So if I have the particles of the solvent attracting together with a strong attraction force for the solid particles to break them and just replace this bond, I will have undissolved solid. Like in that case, I could see that the solid particles just precipitate or accumulate in the middle of the solvent and doesn't dissolve because they are unable to break the bond between the solvent particles. But in the other case here, we could see that the particles of the solvent can break the particles of the solid can break the bond between the solvent and just replace them, and instead we will have solvent solid attraction. So if I have solvent solid attraction higher or bigger than the solvent attraction, I will have a completely soluble solution. But if I have the other way around, I will have not completely soluble solution but immiscible solution. So we could say that the similar intermolecular force would result in miscible solution. In case of octane and heptane, they have the same intermolecular forces, so they can dissolve together and form miscible solution. But for water and octane, they will have immiscible, they have different intermolecular forces, so they will have immiscible solution. For octane to dissolve in water, it have to overcome the hydrogen bond between the water molecules, while octane itself have a very weak London force. This is why octane cannot break the strong force between water molecules, hence it is immiscible in water. When I dissolve any solid in water, it either form what we call electrolytes or non-electrolytes. If it is electrolytes, this means the solids that I'm dissolving will just will be dissociate into anion and cation, while for non-electrolyte it will not dissolve into anion and cation. So the ability to form anion and a cation will be a result will result in the flow of current. So the current, if I have a current that I pass through a solution, if it is completely dissociate, those particles which dissociated will be able to flow the current through the solution. Like in that case, we could, but in the middle case, you could see the very low luminescence of the light, because it is the electrolytes, the solution, the solid doesn't completely dissociate into the solution, and this will lead to a very low formation of anion and the cation, and the low number of anion and the cations that can carry that charges through the solution will lead to a very limited flow of current. This is why the luminescence of this lamp is less. While if it doesn't dissociate at all, like in that case, no dissociation happens, no flow of the current will occur in that solution. This is why the lamp will not light at all. An example for some electrolytes is the dissociation of sodium chloride in presence of water, of course, into anion, which is the sodium, plus cation, which is the chlorine. While example for the non-electrolyte would be urea, which in presence of water will remain the same and nothing will change for urea. Here are few examples for some strong electrolytes, weak electrolytes, and non-electrolytes. You have to remember, for strong electrolytes, it will be able to flow the current very strong, and I will have strong luminescence for the lamp, while weak electrolytes would give me a very weak light due to the presence of less amount of cations and anions. And for non-electrolytes, there will be no flow of current. We use some terms when we explain the dissolving of solute in water. Usually we name this process to be the hydration. So the hydration process is dissolving ions or surrounding the ion by water molecules. And it will be arranged in a specific manner. So if I looked at the hydration of sodium chloride into sodium ions and the chlorine ions, I could see here is that the sodium ions will be surrounded by the water molecules, and the chlorine atoms will be surrounded by the water molecules. This is what I call hydration of the sodium and the chlorine ions in water. For hydration, the hydration will prevent the cation and the anion from combining back or coming back together. This is why both of those, anion and the cation, will be just separated and just be scattered in the solution. In my next video, I will talk about molecular equation, ionic equation, and the net ionic equation. See you next time. Thank you and goodbye.